Just to give everybody a brief overview, just in case you might have forgotten a little bit about your series from Calculus 2. One of the things that we like to use power series for is to represent transcendental or even other sorts of functions, like for instance rational functions, trigonometric functions, etc. So I put together a list of just a few, and there's many more, but I put together some of the more common types of transcendental functions and their power series. And I just wanted to use and show why we're going to use a power series. In other words, what are they good for? And kind of just go back over some of the most fundamental things of a power series. So I'm going to pick on this e to the x because e to the x is one of the easiest ones to work with, quite honestly. And it's something that we use pretty often. So you might remember that there is this thing called an interval of convergence. And that basically means what numbers is the power series valid for x. And sometimes it's all real numbers, sometimes it's not. And that's going to be important for us because if we need to find a series solution about a specific point, we need to make sure that the power series is actually valid around that point. So I'm going to sort of pick on this e to the x, and I'm just going to drop it down real quick just to show you, just to remind you guys of stuff from Calc 2. So here's our power series for e to the x. And let's say for some reason you wanted to find the interval of convergence. Well, remember, interval of convergence, you can use one of those tests. And remember, you had a lot of tests. So you might have had like an alternating series test, ratio test, root test, comparison test, etc. All those tests. We're not going to have to do that in this course. But in future courses, you may need to make sure that your power series is convergent around the specific point. So just to remind you, let's say we wanted to take this series and see where it's convergent. Okay, so remember, you could use the ratio test. And a lot of times when you have factorials in your expression, the ratio test is a pretty good giveaway. And remember, ratio test says that you're going to take the limit as n approaches infinity of a sub n plus 1 divided by a sub n. And you're trying to figure out when that limit is less than 1. All right? So what values x can you plug in so that limit was going to be less than 1? So if we set this up, just to find the interval of convergence, we already know what it is, but just reminding you of how to find it. Lim as n approaches infinity, so we're going to put n plus 1 in first, so x to the n plus 1 divided by n plus 1 factorial divided by x to the n divided by n fact. Alright, so we're trying to figure out when that is less than 1. And if we can figure out when that's less than 1, it's convergent. And so we can just do some algebra magic on this. To clean up the complex fraction, we multiply by the reciprocal. So I'm just going to multiply by n fact over x to the n. And on this expression, what I'm going to do is I'm just going to factor off some of the factors that are necessary to cancel. So remember, x to the n plus 1 can be written as x to the n times x to the first. N plus 1 factorial can be written as n plus 1 times n factorial. And the whole reason I broke those off as such is because now you can see, oh, okay, well, those cancel and those cancel. So we're really just left with a really nice limit. We're left with the limit as n approaches infinity of x over n plus 1. And we know that as n goes to infinity, that the denominator is going to get infinitely large. And so anytime you divide x by infinity, it's going to be 0. So we get 0 less than 1. And so that means that the interval of convergence is going to be all real numbers. And the question is, okay, well, how do we use a power series? So let's define a function. Let's just call it t sub n of x is going to be equal to our series n equals 0 to some sort of infinity, or let's just say n equals 0 to I, some value I. And actually, let's just call this t sub I. X to the n divided by n fact. All right, and let's say for some reason I want I to be, let's just say 1. All right, so Probably going to have to clear off some room here. So let's just get a little bit of room here. And so t sub 1 of x is going to be equal to the series n equals 0 to 1 of x to the n over n fact. And if I just write out the first two terms, that's x to the 0 over 0 fact plus x to the first over 1 fact, or 1 plus x. All right. And remember, this is used to approximate e to the x. So we're using the function, the polynomial function 1 plus x to represent e to the x. How can we see what they look like? Well, we could just look at the graphs. All right, and I'm going to graph those both on the same plane. And if I do so, this is, oh, it should have appeared in there. Sorry, let me try again. Let's see if I can get this to appear in here. Yep, this is what it looks like. All right, it's okay. I mean, like right around the middle, right around the intercept, it's not a bad representation for there. All right, but when we start getting like up here, like maybe when x equals 2, it's not a really good representation. All right, so how do we get a better representation? Well, we start using more values. So we start maybe plugging in maybe something like t of 3 or something like that. All right, so let's see what happens. So if I plug in maybe t, let's say 2 of x, that's going to be equal to 1 plus x squared over 2. So I'm just writing out 0, 1, and 2 this time. All right, so now we have a quadratic to represent the function. Let's see what that looks like. And it's still not too bad. I mean, right around the middle. Looks pretty good. And then when you start getting like around x equals 2, it starts becoming noticeably divergent. So the polynomial's pretty good from maybe something like -1 up to +1 or something like that. So let's see what T3 and T4 might look like. So I'm trying to get rid of this and it doesn't want to go away. There it is. So T3 of x, we're just going to add one more term. And now remember, it's going to be x cubed not over 3 but over 6, because 3 factorial is 3 times 2 times 1. All right, and all we're doing is we're just subbing everything back in to this expression each time. All right, and as you can imagine, this is going to be a pretty good representation. All right, so now it looks like around 2, yeah, this is pretty good. All right, so maybe right about here, it's a decent representation. All right, not really great, but not all that bad either. And what we remember from Calculus 2 is that the more that we increase the power of the polynomial, the better the representation is going to be. All right, so let me just do T4 just to show you what it looks like. In fact, maybe we can do T5 just to kind of be done with this, just to show you how good these representations can be. So T5 of x, a 5th degree polynomial, is going to be equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. So that's 4 factorial, and then x to the 5th over 120, which is 5 factorial. All right, and as you can imagine, we're going to get a really good representation. All right, so here's T5, and T5 looks great, as long as we're not going back. All right, but at least for the positive representation, it looks great. And so that's the power, no pun intended, but that's the power of the power series, is to be able to use a nice and easy polynomial representation to represent these transcendental functions. And that's what we're going to do with our differential equations. All right, so we need to make sure in real life when we get our solutions that the power series is indeed convergent. All right. Now the good news is, because we're finding polynomials, the series is probably going to be convergent all the time. All right, so just keep that in mind for those of you that are going to be using these differential equations and these series solutions later in your careers, that you always want to make sure that it is convergent and that the graph looks like it, in other words, it looks like it should be something that exists with respect to this solution.